In this video we're going to discuss about actually the different unit cells, okay, and try to calculate the number of atoms present in those unit cell. Okay, so the objective of this class is that actually we have to find out, or we have to calculate the number of atoms present in a unit cell. Okay, so now the thing is that we have many different types of unit cells. Okay, so from the previous classes we have some idea that total 7 crystal systems are there, no? Which are cubic, orthogonal, monoclinic, tetragonal, and etc. Okay, so total 7 crystal systems are there. Again, in this 7 crystal systems, again, Bravais total, how many Bravais lattices are there? Total 14 Bravais lattices are there. Bravais lattice. Total 14 Bravais lattices are present. Okay. Again, we know that the 7 crystal system is classified on the basis of what? On the basis of the parameters of characterization. No? So those are what? The edges A, B, C, and angles alpha, beta, and gamma. Okay, so the 7 crystal system is actually classified based on these parameters. And the Bravais, in case of Bravais lattices, these Bravais lattices are actually classified on the basis of the arrangement. Okay, arrangements of the constituent particles. Okay, so mainly or basically there are total 4 types of different arrangement of that constituent particles are observed in a crystal lattice or crystal structure. Okay, or you can say that in a unit cell. Okay, so the first one is your primitive, or sometimes it is known as simple unit cell. Okay, so in unit or in this unit cell, that means primitive or simple unit cell, only the corners of that unit cell is occupied by the constituent particles. We have already discussed this part now. Second is your body centered unit cell, where additionally one constituent particle will be present in the center of the bodies of that unit cell. Okay, and third one is face centered, where 2 opposite faces are all the 6 faces are occupied by total 6 additional constituent particle. Okay, and number 4 is your in centered, where 2 opposite faces are actually occupied by 2 additional constituent particle. It may be atoms, molecules, or sometimes ions. Okay, but here in this actually in this video we are going to basically discuss, or we will basically try to calculate the number of atoms which are present in this type of unit cell. So at first we are going to discuss about the primitive cubic unit cell. Okay, cubic unit cell. So we are here specifically we're going to discuss about primitive cubic unit cell. So now we know that in case of primitive or simple, okay, so in case of primitive of simple unit cell, total the 8 corners of the, let's suppose this is the unit cell. Okay, the 8 corners of that unit cell will be occupied by the constituent particles. Okay, so 8 constituent particles will be there in the that corners. Okay, so here actually in this case the constituent particle is your atom. Okay, so let's suppose the constituent particle is your atom, and there are actually this point or these sites are known as what? We already know that these sites are known as your crystal site or crystal point. Okay, so here you have to remember some point. Okay, the point A is that this points, okay, this crystal site or this crystal point does not represent the actual size and shapes of the constituent particles. So please remember this point. Okay, so first point is what? The crystal site or you can say the crystal point also. Okay, the crystal site does not represent the actual size. Okay, the actual size and shape of the constituent particle. But here we considered already that the constituent particle is your atom, so you can write the shapes of the atom. Okay, so we need a different image, okay, of this this is what? This is your actually unit cell, no? This is actually unit cell. Okay, so actually this unit cell which actually we represent this unit cell by using what? Some point, no? And this actually representation is known as your open structure. Okay, so remember this point. Okay, so this is actually known as open structure of what? Open structure of your this primitive cubic unit cell. Okay, so since these are actually not this will not going to represent the actual shape or actual size, so we need a different structure of or different representation of that unit cell, which is actually shown in the figure 1.9b. okay, so here if you notice this figure, then you able to know that here, you know, this point is actually represented by this sphere. Okay, understand? And this point is represented by this sphere. Okay, so similarly there will be total 8 sphere, okay, which are actually, you know, packed with its packed such a way that the minimum, there will be a minimum actually space left, or we can say that space filling structure. So this structure is known as space filling structure. Okay, structure. Okay, so this is actually your space filling structure. Understand? But the thing is that what is our aim? Our aim is to calculate the number of atoms present inside. Okay, inside this unit cell, not outside. Okay, so when we are talking about actually, if you only consider this point, let's suppose this this point, no, but here there will be a big atom, no, there will be a big atom here, there will be also a big atom, but only a part of this atom will be inside this unit cell. The other parts will be outside the this, you know, this unit cell. Actually we can understand this actually this, you know, fraction of these atoms which are inside this unit cell by using the figure C. Okay, and this figure C is actually known as actual portion of atoms belonging to one unit cell. Okay, so here if you see this you know, figure, which is actually, I am taking this figure in from your you know, class book, NCERT book. You see here from this one, if you notice this part only, this, let's suppose this only 1/8 portion of that atom will be inside this this unit cell. Okay, similarly for the other atoms also. Okay, so to calculate the total number of atoms which are inside this unit cell, we can take you can actually use this technique. Okay, so how many total? So just we can do is like that, the total number of atoms present in the unit cell can be calculated as given below. Okay, so we're going to now calculate the this one. Okay, so now let us calculate this one. Okay, so here we know that total how many corners are there? Total 8 corners are there, no? So your total number of atoms in cubic unit cell is equal to, so total 8 corners will be there. That means in each corner total 8, each corner 1 atom will be there, no? So total 8 atoms present in 8 corners. Understand? Okay, so 8 atoms will be present in 8 corners. Okay, understand? But here the thing is the whole atoms will not be inside that inside that unit cell. Okay, only a portion, and that portion is actually 1 by 8. Why 1 by 8? Because one atom is actually distributed between 8 unit cell. Okay, so 8 unit cell, that's why we only 1 by 8 portion of one atom will be inside that inside that unit cell for one corner. Okay, but here how many corners are there? Well, 8 corners are there, so 8 into 1 by 8 atoms will be present in that unit cell. Understand? So total how many? One atom will be actually present inside that unit cell. Hope you understand this point. Okay, okay, so here in case of cubic unit cell, the total number of atoms which are present inside that unit cell will be always 1 in case of primitive. Okay, so now let us discuss about the second one, which is your body centered cubic lattice. Okay, second one, which is your body centered cubic unit cell. Okay, so here again we know that the body centered unit cell, actually additional one constituent particle, or here since we are considering only atom for that constituent particle, so one additional constituent particle or atom will be in the body center of that unit cell. Okay, it will be actually like this. So this is actually total 8 corners will be occupied by total 8 atoms, and additionally in the center of this cube. Okay, let's suppose this is your center. In the center of this cube, one additional atoms will be present. Okay, so now for this one again we can calculate the the number of atoms present in this unit cell. Okay, by using that previous technique. But here again this is actually, this structure is already let's suppose A, and this is actually what? This is your open structure. Okay, again the same thing, open structure. This is the open structure, and when we replace this lattice site by actual atom or actual atom, then that structure will be known as what? Your space filling structure. Okay, and to calculate the number of atoms, or to represent the number of atoms inside that cube, we actually use the structure C. Okay, so we have this information. Okay, now what we have to do? We have to calculate the number of atoms present in that unit cell. So for that, what we can do? So for that one, actually, suppose what we have to do, our aim is to calculate the total atoms present inside. Okay, inside of the body centered cubic lattice, and here it is known as BCC, body centered cubic lattice, or body centered cubic unit cell. Okay, so here also the total number of atoms present inside the body centered cubic lattice will be what? Or body centered cubic unit cell will be first always again the same will be there, na? Total, you see here total 8 corners will be occupied by the 8 atoms. So 8 atoms in each 8 atoms in 8 corners. Okay, 8 corners, and 1 by 8 we have to multiply by 1 by 8, because 1 by 8 per corner atom. Okay, that means one atom will be distributed only 1/8 part of that atom will be inside that unit cell. Okay, I hope you understand this point. Plus this is for the first one, that means for the corner, only corner. This contribution is coming from where? Only from the corners. Okay, 8 corners. And additionally we know that one atoms will be present inside that that center of that unit cell. So there will be additional one body centered atom will be present. So total how many atom will be present then it will be your, from this part corners, it will be 1 plus 1 atoms will be coming from where? The body centered. Okay, so total we have 2 atoms inside that BCC unit cell. Understand? Now coming to the next one, which is your face centered cubic unit. Okay, now the third one is your face centered cubic unit cell. Okay, so in this case actually face centered cubic unit cell, we know that, let's suppose this is your unit cell. Okay, that cubic unit cell, and for the simple one we know that the total 8 atoms will be present in the 8 corners. Okay, and for body centered one one additional atom will be present at the body center of that unit cell. But in this case actually face centered, here how many faces are there? This is one face. Okay, this is one face. Let's suppose this is one front face. Okay, this is the one face, upper face. Okay, here this is the below, this is the face below. Okay, again here also one face, here also one face. Total number of faces will be 6. Okay, 6 faces will be there. So in each phase one atoms will be present in the center of each phase. Okay, so in the face centered cubic unit cell, the center of each phases will be occupied by that one total 6 additional additional atoms. Okay, but here the thing is that in a phase, let's suppose this is one atom. Okay, so in a phase actually one unit cell will be present here. You see the next unit cell will be like that, na? Because in a crystal there will be many unit cell, repeating unit cell. We already discussed this part also. Okay, in a crystal there will be there will be many unit cell present in the 3 dimension. Okay, so in, let's suppose this direction 1, this is the next let's suppose unit cell. Okay, so in case of that atom, that atom will be divided half. Okay, you see, one half will be present inside this unit cell and the other half will be present inside this unit cell. Okay, so that means one half of contribution will be coming from one atom for each phases. Okay, understand? For this phase is one half, for this phase is one half. So total 6 phases, 6 into one half. That means 3 atoms will be there. Okay, 3 atoms will be coming from the phase. That means the contribution from the phase atoms will be 3. Understand? So we can use this concept now to calculate this. So the total number of the atoms present in, so please write this all the things, okay, in your copy. Okay, so total number of the atoms present in the this is actually known as face centered, na? So FCC, you can write FCC, face centered cubic lattice. Okay, FCC is equal to, you can write the, for the same for the corners it will be same. Okay, 8 into 1/8. So I am not going to discuss this part, already discussed in the previous two. Okay, so 8 corner and 1/8, because 1/8 contribution from each one atoms. Okay, in case of the corner, so this will be actually the contribution from corners, corners. Okay, some corners atoms, and plus total 6 atoms will be present in the total 6 phases into 1/2, because this is 1/2. Why? Because one half of contribution will be coming from one atom. Okay, understand? So your total will be is equal to 1 by this one, actually 1 plus here 3, that means total 4. 4 atoms. Understand? So that means total 4 atoms will be present, or 4 atoms will be present inside what? One face-centered cubic unit cell, or FCC unit cell. Understand? So remember this, these three, actually 3 topics. Okay. The first one is what? That simple cubic lattice, then BCC, then FCC. Okay. So this is important for your exam also. Okay. So maybe some 1 marks or 2 marks question maybe come from this portion. Okay. So now we're going to discuss about a new topic. Actually, this is known as close-packed structure. So we're going to actually discuss in that portion about the packing, how the constituent particle is going to arrange in different directions. Okay. So let us discuss about that. The next topic is actually your closed packed structures. Okay. So here we already know that in case of solid, the constituent particles will be close to each other, and in case of liquid they are slightly far from each other, and in case of gases they are very far from each other because of their intermolecular force of attraction. Okay. So in case of solid, actually the constituent particles are very, very close to each other. Okay. They are just actually they are touch each other. Okay. And they actually packed such a way that they actually leave a very minimum or very small empty space or vacant spaces. Okay. In between the packing. Okay. So and actually we will going to use two actually we will going to use, or we will going to consider that the constituent particle will be your identical to each other. Okay. So if one atom will be there, the same atom will be near to that atom, and another atom, another same atom will be near to that other atoms. Okay. It will be like that. And also additionally we have to consider that that atoms or that constituent particles will be hard sphere. Okay. But actually this is not true. Okay. Actually the constituent particle, that means the atoms or molecules or ions, are not so hard, because actually what is atom? Actually one positive, that means nucleus will be there, and there will be some electrons cloud, that means the probability of finding the electrons in the orbit. Okay. There will be some cloud of electrons will be there. So actually some one electron, there will be some, they are actually not so hard. Okay. There may be some polarization. Okay. That means the shapes of that orbit may not be totally hard sphere. Okay. Understand? But here actually we will going to use this two actually point or two concept to to understand the close packed structure. Okay. So actually the constituent particles may be packed in 3 different ways, and this is actually basis on their dimension. Okay. What is the meaning of dimension? Direction. That means 3 directions, x, y, z direction. I think you you have this knowledge of this coordination. Okay. That means the axis, the concept of axis in from mathematics. Okay. And geometry maybe. Okay. So here you see, let's suppose we know that we have 3 dimension. Okay. In case of Cartesian coordinate, let's suppose x, here this is z, let's suppose this is y. That means it will be like this. Okay. If you consider let's suppose here one axis, here one axis. So this is, let's suppose this is your x axis. Okay. This is your x axis. So if you consider the only one dimension, if you're going to consider only one dimension, then the constituent particle will be only arranged in one way. Okay. Only in a line. That is the one direction. Okay. So if you consider one dimension arrangement, then it will be what? In one line. Understand? And if you are going to consider it in 2 dimension, then it will be like that. Okay. It will be like that. That means it will become a plane. Okay, so it will be the atom can be coming from this axis or this axis, or in this plane actually, in this surface actually the atom can be arranged. Okay, but if you consider this in 3 dimension, then it will be like what, some upper, like this one will be there, no? Understand? So like this one. So atom can be, or constituent particle can be come from upside, or arranged from upside also. So it will be 3 dimension. Okay, so we have to consider actually first we are going to discuss about this, you know, this 1 dimension, then in a plane, that means 2 dimension, and 3 dimension, that means it may be a cube. Okay, understand? So we're going to discuss about this one by one. Okay, so now first discuss about the 1 dimension. Okay, so in case of 1 dimension, let's suppose only x-axis. Okay, so we can use any one axis. Okay, it may be x-axis, it may be y-axis, or it may be z-axis. So let us first consider the 1 dimension. Okay, wait. So let us first discuss about the 1 dimension, that means the closed packing in 1 dimension. Okay, so 1 dimension means 1 direction. Okay, so here actually the way of arranging spheres in 1 dimension, okay, that means in 1 axis. So here we can understand this concept by using the figure 1.13. okay, this is from your book. Okay, 1.13, and here actually it will be what, it will be actually 1 axis. You see, this is only actually let's suppose this one is your 1 atom, the another atom will be come from only 1 axis. Okay, it cannot come from the other axis, so only 1 dimension, so it will be this one, and the third one will be coming from this way. That means the packing of those constituent particle will be only along the axis. Understand? So it will be like this one. So in this arrangement actually each sphere is contact with how many other sphere. You see, if you consider this sphere or this constituent particle, then this constituent particle will be touch with this one and this one. Okay, so this actually, that means the number of nearest neighbors of 1 particle is actually called what, coordination number. Okay, so remember this one. What is coordination number? Coordination number. Okay, so the coordination number is the number of atoms which are actually nearest. Okay, nearest with 1 constituent particle. That means if this one is the 1 constituent particle, then how many constituent particle will going to near with this one? That number will be the coordination number of that constituent particle. Understand? So here only 2 are actually, here you see only 2 of them are actually near to this constituent particle. So the coordination number will be 2. Understand? Clear? Very simple. Okay, so the coordination number for close packing in 1 dimension, only 1 dimension. Okay, 1 dimension is 2. So now let us discuss about the second one, which is your close packing in 2 dimension. Okay, so the second one is B, close packing in 2 dimension. 2 dimensions. So 2 dimension means it may be xy. Okay, it may be xy, it may be xz, that means upside. Okay, xz. Okay, understand? Or it may be yz. That means it may be, actually it is 1 plane. Okay, so it will be slightly harder than actually the 1 dimension case. So here in 2 dimension actually there are 2 ways, actually 2 different possible ways are there to arrange themselves in 1 plane. Okay, so the first one is represent in figure figure 1.14. Okay, 14a. So here here 1.14a. So here if you see, let's suppose this is your x-axis and this is the y-axis. Okay, suppose that means x and y. Okay, so first will be the first atoms, and that means the constituent particle will going to packed in one dimension. Okay, then the another one will be, the another row, that means it will going to form a row. Okay, this is suppose this is the first row. Okay, and the another row of the constituent particle will be exactly above those of the first row. Okay, that means let's suppose this is A. Okay, this row is represented by the capital A. Then the other row will be also capital A, because this is exactly same and exactly exactly above those the first row. Okay, actually this sphere of the two rows are aligned. Actually how they align? Actually they align horizontally, okay, as well as vertically. Okay, if we call this first row as A, okay, A type row, then the second type of row will be the same, that means it will also be A. Okay, understand? So here you see, here this part, if you want to calculate, or the thing is, here you see that this is A, again A. So actually this type of thing, this type of arrangement is known as A type of arrangement, or A type of alignment. Okay, so A type of arrangement, or you can say alignment. Okay, arrangement is good term. Okay, arrangement. Okay, understand? So now let us calculate the number of coordination, that means coordination number. Okay, so now if you consider only one, let's suppose this atom, okay, or this constituent particle, then you see this constituent particle is surrounded by how many particles? Here you see 1, 2, 3, 4. That means it will be touched, that means this constituent particle is actually touched by total 4 constituent particles, or it has total how many neighboring constituent particle, nearest neighboring particle, total 1, 2, 3, 4. Okay, that's why the coordination number in the close packing in 2 dimension, if the packing arrangement is A type, then the coordination number will be what? The coordination number will be your 4. Again, if you join, okay, if you join the this 4 in immediate neighboring squares, then it will become what? A square. You see, it will become a square. Okay, and actually because of this shape, or this packing is called square close packing. Okay, so this is known as what? Square close packing. So we can actually term this one as a type of packing arrangement, or we can even say that this is your what? This is your square close packing. Now let us discuss about the second probable way. Okay, so in this way, in this actually arrangement, or in this close packing, so actually here let's suppose this is your the arrangement. Okay, so here let's suppose this is the first row. Okay, so the second row, we can arrange the second row, or we can pack this second row staggered manner. Okay, that means staggered to the first layer, and the next, that means let's suppose this is your A. Okay, this layer is your A layer, and the second layer will be what? Your, because this is your staggered, so it will be different than this one, so it will be your layer B. Okay, again the third one will be the staggered of that second one, and the third one will be actually since staggered to the second one, and the first one is staggered to the second one. That means the A, that means the first row and the third row will be the same one. Okay, because they will be, this atom will be exactly above this atom. Okay, so this again the fourth row will be what? Again it will be B. That means AB. Understand? So that means this type of arrangement, or this type of packing result the AB type of arrangement. Understand? And if you notice this, or if you want to calculate the coordination number, then here you see one atom is actually actually one atom is surrounded by nearest, how many atoms will be there? Nearest total 6 atoms will be actually near to that one atom. Understand? That means the coordination number for this type of close packing will be your 6. Actually regular hexagon can be, if you join that neighboring atoms by using some lines, then it will give you what? A regular hexagon. So sometimes this packing is also known as what? Hexagonal close packing, or sometimes, because this is a two-dimensional arrangement, so it is known as two-dimensional hexagonal close packing. Understand? So we can term this packing as a AB type arrangement in two-dimensional, and also we can use two-dimensional hexagonal close packing. Moreover, if you notice this this figure, be carefully, then here you see some void space or some empty spaces will be left, okay, in this close packing. So actually the shape of this empty spaces is actually triangular in shape, na? And here actually two types of void space are observed. In one row, the apex of the triangles are pointed downwards, and the next layer, the apex of the triangles will be pointed upward. Okay, so this is all about packing in one dimension and two dimensions. And next topic we will going to discuss about the close packing in 3 dimension. Okay, so it will be slightly complicated because it is 3 dimensional, because it is x direction, y direction, and also the z directions. So it is slightly complicated, but if you understand these two, actually the 2 dimension, then it will be easy for you to understand the 3 dimension.